right, yeah, so I'm going to talk to you about the sun, and I'm going to talk to you about how we can use our proximity to the sun to get a truly global and three-dimensional view of a star. I'll talk mostly about why we have to go to the sun's poles in the near future to really make a breakthrough. I'll also talk a little bit about how that could happen towards the end of the talk. But as you can see, I took as my title Beyond Flatland. And Flatland, as you probably know, is a novella, a story about a square who has a sequence of dreams. And he wakes in the middle of the night, he dreams that he is in Lineland, in a one-dimensional world. And so he tries to explain his two-dimensional world to the lines, and they don't know what he's talking about. And then the next night, he has a dream where he's visited by a sphere. And the sphere takes him to Spaceland and actually teaches him about the third dimension by letting him fly up and down and see her cross-section circle, shrink, and increase. So I think you'll see why I found this a motivating idea. And of course, we want to go beyond Flatland, and we want to study a star of many dimensions. And the thing about the sun is that it's all about magnetic fields with the sun. Magnetic fields are what lies behind the incredible dynamics, the coronal mass ejections, the flares. It's also the reason that despite all of our observations we've been doing over the past decades and centuries, we keep finding new mysteries to solve, new magnetic mysteries. And what do I mean by that? Well, let me actually take a step back, and let's go to the flattest flatland view of the sun we can imagine, the kindergartner's view of the circle and the spikes. And this view of the sun, of course, this perfect, unblemished sun, was very quickly put to rest as soon as people started observing, and I'm talking about 4th century BC, Chinese astronomers seeing sunspots. And then, of course, when we got telescopes, it really became clear that the sun is not this simple structure. The sun has sunspots. And this is Galileo with his telescope. He actually was not the first one to observe sunspots. It was Scheiner. But Galileo correctly interpreted the fact that you could see these black splotches move across the disk of the sun. Scheiner thought they were very, very close planets. But Galileo realized it meant that the sun was rotating. And then as we got more and more data over the next decades and centuries, it became clear that there were really interesting patterns. There were cycles. Every 11 years, the number of sunspots would wax and wane. And in 1904, the wife and husband team of Annie and Walter Maunder discovered this beautiful pattern, the butterfly pattern, by painstakingly drawing by hand, taking turns, drawing by hand, the location of the emergence of sunspots, and showed that that location migrated toward the equator over the course of the 11-year cycle. So there are these patterns, these intriguing patterns. And then these patterns continued over many, many decades and centuries. And on the top, you're seeing the latitude versus time plot. On the bottom, you're seeing the number versus time. And you can see that there's an incredible regularity about it, and yet it's not perfect. It's about 11 years, but it's not exactly 11 years. There are some sunspot maxima with many more sunspots than others. And George Ellery Hale, in 1908, I think, realized that what we're looking at is, of course, a magnetic mystery, because these sunspots were magnetic. They were thousands of times stronger than anything measured on the Earth. And so this is the magnetic mystery that these observations keep pushing toward us. How is the sun creating and sustaining these cycling magnetic fields? And why is it almost exactly, but not exactly, 11 years long? And these are, of course, the questions at the heart of the solar dynamo. So fast forwarding to space-based observations, we started having helioseismology, and actually ground-based as well. By measuring oscillations on the surface of the sun, it's possible to probe inside the sun, and in fact, to look at the flows, rotation, and shear. And you can see here, this is the sun's rotation pattern. And we already knew from sunspots that that rotation that Galileo marked is not constant. The sun's not rotating as a solid body. It's differential rotation. It's rotating faster at the equators and the poles. What helioseismology let us do was to look inside the sun and see that faster rotation at the equator, slower toward the poles, persisted down to a layer at the base of the convection zone where there was a strong shear. But we don't actually know what's happening at the poles in this rotation profile, because the global helioseismology from the Earth, you can't resolve those flows at the pole. We also don't know what's going on in terms of the magnetic fields at the poles. This is the photospheric field. It's a really important boundary condition on the heliosphere, the entire solar system magnetic field from below, and on the dynamo from above. So it's crucial, but we're looking at a sphere, and we have all sorts of projection effects which causes problems. In fact, it introduces another solar magnetic mystery that won't go away, which is, why is the magnetic field that we try to get some idea of the polar field. We know the Earth goes up and down in its orbit relative to the sun by 7 degrees, so you get a peak over the poles twice a year, right? South Pole, North Pole. So people have made kind of ad hoc correction factors. There's ways of trying to get a sense of what that polar field is. But why is it that whatever we do, we end up with a factor of 2 or more difference between what the solar magnetic fields in the high latitudes seem to be telling us and what our spacecraft measure in situ in the solar wind? So this is another mystery. And here's an example of taking a boundary condition and playing around with it. On the left, this is the standard processing. This is kind of the best practices of what you would say the polar field would be based on the ecliptic observations. This is now putting in a top knot of strong field that we wouldn't be able to see from the ecliptic. And there's the differences between these two is putting in a patchy top knot or putting in a solid top knot. Both of these are consistent with what we observe in the solar wind. And all 3 of these are consistent, if you rotate the sun, with what we see at the Earth. But we don't know. Okay, so how would a polar view help answer this question of what the magnetic fields are? Well, first of all, of course, we'd be able to look right down on the magnetic fields. It's basically, the observations that are good are within about 60 degrees of disk center. So if we could get high enough up, we could look down on it. And this is a simulation showing that strong, open monopolar field at the pole. And these are magnetic lines of force. And so you can see that if we could look at, we could see not only the magnetic field, but if we had an extreme ultraviolet imager, we could see the coronal hole. Because where the magnetic field is open to the solar wind, the extreme ultraviolet images show us that it's dark. It's a coronal hole. So that would be wonderful. We also could get a better view of the closed magnetic fields, the fields that aren't open to the solar wind, but closed down to the surface of the sun. These are really interesting because this is where magnetic energy is stored and builds up and explodes in these coronal mass ejections. So that would be really good to be able to get that view from above. And that view from above, or sunny side up view, as I like to call it, is really important. These, of course, are both simulations, right? So on the right, what you have is a simulation of a coronal mass ejection viewed from above. And the thing is, right now, we see these things go out, but we don't really know how they're interacting in longitude. We can't see that from the ecliptic. So that kind of interaction, and also CMEs, you get a CME in one place, you can get an effect far, far away from it. Oh, and I'm saying CME, coronal mass ejection, not CMB. I realize in this crowd, I really need to make that clear. Coronal mass ejections, one of these on one side of the sun could affect the other. If you're looking from above, you can see that. Also, this is actually a schematic, it's a simulation, but you're seeing velocity. So here's that ejection coming out. The yellow is the Earth. When one of them is coming right at the Earth, that's actually the hardest to resolve its velocity, its trajectory, because it's what we call a halo CME. It's actually kind of the worst view. But if you could view from above, you'd be seeing all of those CMEs moving through the solar system in all directions, towards the Earth, towards all the planet. If you've got astronauts going to Mars, it'd be nice to know what's coming in their direction. So it's really quite a lovely view from that point of view. But I really want to come back to the idea of the solar dynamo, because I think that's the fundamental physics that's driving all this. If we could observe the poles, we could observe the magnetic fields at the poles, and we make assumptions about what's happening on the sun, that the magnetic field that comes out through the sunspots is passively moved to the poles, and that's what creates this coronal hole. But we don't actually know. There could be sources and sinks that we're not observing. We also from the poles could resolve the flows, and this is very important. This is the north-south flow, or the meridional circulation. This is why we think maybe there's a passive transport, because what we observe from helioseismology and other methods is that there's a conveyor belt that transports flux from the active regions, the sunspots, toward the poles. But again, we don't know what's happening up here. There could be a countercell pushing the other way. It could come and go. This might be partly why there's not an exactly 11-year cycle. And that differential rotation, that's the east-west or toroidal observation that I mentioned earlier. That we don't know at the poles. We know that it's slower at the equator than the high latitudes, but it could spin up again. There could be a polar vortex. We don't know because we can't observe from the ecliptic. And the reason we need to know all this is because there's a real dance of the solar dynamo between all of these flows. We know that the dynamo is basically all about taking the poloidal magnetic field at solar minimum, the sun is pretty much like a dipole, and transforming it into a toroidal magnetic field, which we see in the form of emerging sunspots, and then it has to go back again, and then so on and so on and so on. And so one of the simplest explanations, there we go, is that it's just that differential rotation that's winding up and translating the north-south to the east-west. And then it also actually strengthens it because it gets sheared down there at the bottom of the convection zone. It buoyantly rises. It rotates because of Coriolis effects. You get a tilt. You create some poloidal magnetic field. It goes on the conveyor belt. And then there's the part which we don't know because we can't observe it. Somehow it goes back down, maybe on another part of the conveyor belt. And that's a lovely concept because that would explain why it's 11 years, because it would be that transport, that conveyor belt that sets the clock. It explains why a measurement of the sun's polar magnetic fields, as best we can get it, at solar minimum is actually a pretty good predictor of how strong the next sunspot maximum is, because it's a recycling of that field from poloidal to toroidal. But it's not the only possibility. In fact, there can be a localized, more dispersed transfer from poloidal to toroidal going on throughout the global convection zone. And if that's happening, and these are just little cartoons showing schematically how you might have rotation operating on a poloidal field and creating helicity and creating a twist to create the toroidal field, simulations have shown you can actually form these large-scale structures, toroidal structures, like the active region emergences. So this is a possibility, and it's probably happening for some stars. Because the trick is that whether or not it's this kind of passive transport picture or this dispersed picture has to do with what kind of star the sun is dynamically. And we don't know the answer to that question. The stellar Rossby number is a measure of the influence of rotation on convection. We have a pretty good idea of how the sun rotates. But the strength of that convection is less well known. And so we know that the sun is somewhere in the middle of this spectrum of stellar convective forms. We know it's not non-rotating. We see it rotate. We know it has convection, so it's not rotating so fast that convection is suppressed. But we don't know where. And if, for example, I mentioned that dance, the flows are coupled, the meridional circulation, the differential rotation, the convection. If we observe that polar vortex, the spin-up, that's actually a smoking gun indicator that we are right here at the boundary of the Rossby number 1 in terms of these regimes. If, on the other hand, we see that meridional countercell that might be lengthening the cycle, that's an indicator that we're getting over here towards more rotationally dominated regimes. And that difference matters because it affects, the sun is kind of our best data point for the dynamo, right? Because there's planetary dynamos and there's stellar dynamos, but we have this wealth of data on the sun, and the sun's dynamo is happening on timescales, 11 years, 22 years for the full magnetic closure, much, much faster than, say, planetary dynamos. So this is really important to understand whether we've got our story straight. We need to resolve this. And it also helps us predict space weather. It would be nice to know if it is the more passive transport, there's a possibility for data-driven predictive simulations, for instance. And if we could know in a couple years that it's going to be a particularly active time, that's worth knowing. If we know it's going to be a less active time, that's also worth knowing for astronauts in space, space missions, et cetera. Okay. And so this is the last solar slide I really have, which is just to point that this view also of convection is fundamentally different. If we're towards the rotationally dominated regime, we actually expect not to see convection like the boiling water on your stove, but rotating more in columns. And so looking down on it, we'd be seeing little polar vortices, little swirlies right at the pole. And it turns out that the size of those swirls will tell us more about, will also be an indicator of the strength of convection. So this would be it'd also be really cool to see, frankly, and maybe this immediately makes me think of these pictures, which you may well know, which is these observations taken from the poles above Jupiter and Saturn. And it really indicates just how important it is to get the polar view to get a sense of the fluid dynamics balance between rotation and gravity that goes on in any kind of rotating sphere, be it planet or star. And this is a quote I heard on a radio interview with Steve Levin, which was, every time we look at things in a new way, we find a surprise. We don't actually know what we're going to find at the poles. There's a lot of known unknowns that we can look for, but there's also what we may find. So that's my motivation. And in the last couple minutes, let me just briefly tell you a little about how we can get there. The most obvious way, to my mind, well, until I came to this meeting, is a Jupiter slingshot, because we've done it before. The Ulysses mission went to the poles. It only did in situ measurements of the solar wind. It had no remote sensing observations of the sorts I've been talking about. My own involvement is I was project scientist on the Solaris Mid-X mission, which was in phase A, and unfortunately didn't make it to phase B. Solaris was going to send one of these magnetograms to the poles, as well as an EUV imager, to answer these questions. So that's one way to do it. And of course, if we want to do more, because Solaris there's a big, fat, low-hanging fruit that needs to be picked here that can be done essentially by going over the poles once. But we also need to be there and stay there to look at the solar cycle variation. And the Decadal Survey for Heliophysics has commissioned a study for a constellation, more of a flagship mission, called Firefly. And this would have 4 satellites to get continuous 4-pi coverage of the sun. And it would have more instruments. And then, of course, solar sails. And NASA's Solar Cruiser is a tech demo in development to be launched, I believe, in 2025. It's big, the size of 6 tennis courts, and it's really just to demonstrate that it can go and maneuver in space. And so this is in the works. And then, of course, there's everything that's been talked about at this conference, which I'm really excited to learn more about. And this has been said already. Somebody used this phrase, and I'm using it again. Miniaturization is key, because, of course, for anything we do, even for Solaris, it was crucial to get our instruments down to the smallest possible size. And these slides are just showing what's been done with CubeSats. And you can see that this is different kinds of solar instruments, EUV imagers, irradiance. This is a coronagraph. This is a nice one because coronagraphs traditionally have to be very long because you need to have your occulter very far away from your telescope. This is a CubeSat where there would be a titanium sphere about the size of a tennis ball that would be in formation flying with the CubeSat to create the external occult, which would be very cool. And then, of course, there's Solaris's instrument, the compact Doppler magnetogram, where we made great strides in reducing the mass, the power, and the size, and demonstrated that it was able to handle the high velocities of Solaris, which got to about 20 kilometers per second. And this is TRL-6, and it's been built and demonstrated on the ground. And then the last one I'm leaving you with is a very inspiring concept, which comes out of Lockheed, which is using photonics to build a magnetograph the size of a penny in its diameter and about twice the mass of a penny in total. And this is TRL 3 and 4. It is currently being developed. And it, of course, would be a dramatic reduction and increase in possible options for sending these things on solar sails. So my conclusions, the more we observe the sun, every time we observe something, we learn a new mystery. The dynamo is really the low-hanging fruit. We need more information about the polar fields and the polar flows. And I want to just leave you by saying that we don't necessarily need high-resolution instruments. The science is driven by the vantage. They need to be high enough to be able to resolve these questions, but they don't have to be super state-of-the-art spectral resolution and spatial resolution, et cetera. So this really lends itself well, I think, to the push towards miniaturized instruments, because what we ultimately want is a global and sustained coverage in 4 pi all around the sun. Thank you.